Hello students and followers of my channel. In this lecture, we will see about limit and continuity. Clearly, limit and continuity are fundamental objectives of calculus, and limits are theoretical in nature, but we start with these interpretations. Limits can be used to describe how a fundamental behaviors as an independent variable approaches a certain value. So we have two definitions of a limit, the formal definition and an informal definition. The informal definition is defined like this one. The notation, this expression, the notation lim as x approached a of x is equal to n is read as the limit of the function as x approached to a is L, and mean that the fundamental value of x can be made arbitrarily close to a unique number n by choosing x sufficiently close to a but not equal to a. So as an example, we can give the following examples, and we can form a table to find or to guess on the limits of the function as it approaches to the number. So a is the limit as x approaches to 2 of x squared minus 4 over x minus 2, and b is the limit as x approaches to minus 2 of x squared plus x minus 2 over x plus 2. So clearly, let's see this example. So note that the fundamental, the function f of x, which is defined by x squared plus x minus 2 over x plus 2, is not defined at x is equal to. Clearly, when you are substituting x is equal to minus 2 on the denominator, it becomes 0. So if the denominator is 0, then the function becomes undefined. So for x is equal to different from minus 2, we can simplify the expression for f of x by factorizing the numerator and cancelling with the denominator. So when we are factorizing the numerator, which is x squared plus x minus 2, so those numbers which their sum is 1 and their product is minus 2 is x plus 2 are 2 and minus 2, so minus 1, so x plus 2 times x minus 1 over x plus 2. So cancelling this one, x plus 2 and x plus 2, so we get f of x is equal to x minus 1 for x different from minus 2, because at x is equal to minus 2, it's not defined. So when we are drawing this function, f of x is equal to x minus 1, which is a linear function, which is undefined at x is equal to minus 2, so that at x is equal to minus 2, we make it a whole. So when we are drawing this one, the intercept, so for the function to find the intercept for a point, so for this function f is equal to x minus 1, to find the x-intercept, we make y's value or f of x equal to 0, so x becomes 1, and when to find the y-intercept, we make x is equal to 0, so that we get y is equal to minus 1, so that the x and y-intercepts are 1 and minus 1. So the graph of f is y is equal to x minus 1, which with 1 point removed, namely the point minus 2 minus 3. This removed point is shown as a whole in the graph above. So even though f of minus 2 is not defined, it's clear that we can make values of f of x as x close to minus 2. We went minus 3 by choosing x close to enough to minus 2. So using the table, we can find the values of function as x approach to from the right side and as x approach to from the left side. So taking those points, minus 2.001, its value is this one, minus 2.05, its value is this one, clearly, and at minus 2 it is defined, and from the right, minus 1.99 something, and its value is minus 2.99, at minus 1.995, its value is this one. So clearly from this one, if you approximate this one with one significant figure, so it becomes minus 3 closely, when therefore we can say that f of x approach to arbitrarily close to minus 3 as x approach to minus 2. Or more simply, we can write the limit as x approach to f of x is equal to minus 3, or the limit as x approach to minus 2 of x squared plus x minus 2 over x plus 2 is minus 3. The formal definition for the limit is an epsilon definition or formal definition. So it is defined as let the function be defined on every point of some open interval containing a possibly at A itself, except possibly at A itself. Then the number L is the limit of f of x as x approaches to A. If for every epsilon greater than 0, there exists a corresponding delta greater than such that 0 less than absolute value of x minus A less than delta implies that f of x minus L is less than epsilon. If such a number L can be found, we say that the limit of f at A exists, or limit of f has a limit at A, or we can write the limit as x approaches A of f of x exists and it is equal to L. So using the definition, we can find, we can prove that the given limits of the function is the number is given. So shows that the limit as x approaches to 1 of 2x minus 3, which is equal to 1, which is equal to minus 1. So using the epsilon delta definition, the function is given to x minus 3, and L is given minus 1, and A is given minus, which is 1. So for every, using the definition, for every epsilon greater than 0, there exists a delta greater than 0, such that 0 less than absolute value of x minus 1 less than delta implies absolute value of 2x minus 3 minus of minus 1 is less than epsilon. So we are going to work this side. We are going to work on this side to make similar to this part, so that we can find the relation between epsilon and delta. So rearranging this side, it becomes absolute value of 2x minus 3 minus of minus 1, which is the same as 2x minus 3 plus 1. So it becomes 2x minus 2. So taking 2 as common, it becomes x minus 1, absolute value of x minus 1 less than epsilon. So dividing by 2, you'd get that epsilon. So x minus 1 on both sides, so that we can choose delta is equal to epsilon over 2. Delta is equal to epsilon over 2. So substituting delta is equal to epsilon over 2, you'll get the value of this function. You'll get the limit of the function, so that the limit as x approaches to 1 of 2x minus 3 is equal to minus 1. The next example is the limit as x approaches to 3 of x squared is equal to 9. So using the epsilon delta definition, we can show that the limit of this function is 9. So f of x is x squared, L is 9, and A is 3. So for every epsilon greater than 0, there exists a number delta greater than 0, such that 0 less than absolute value of x minus 3 less than delta implies x squared minus 9 is less than epsilon. Now we should work on this part to make similar to x minus 3, absolute value of x minus 3, then we can find the relation between delta and epsilon. If we can find the relation between delta and epsilon, so the limit of the function exists and it's equal to the 9. So x squared minus 9 is when we are factorizing the x squared minus 9, so it becomes x minus 3 times x plus 3. So it becomes absolute value of x minus 3 times absolute value of x plus 3 is less than epsilon. So clearly x minus 3 is here. So how can we remove this part, x plus 3, which is not a constant? So that to remove this non-constant term, let's choose the first delta. Let's choose the first delta. Delta is equal to 1. So it becomes 0 less than absolute value of x minus 3 less than delta implies absolute value of x minus 3 is less than 1. So by absolute value definition, minus 1 is less than absolute value of x minus 3, which is less than 1. So adding 3 on each side, you'll get 2 less than x less than 4. And we should make, to remove this part, x plus 3, to remove this one part, let's add 3 on each side. So 2 less than x less than 4. When you add 3 on this side, 5 less than x plus 3 less than 7. So 5 less than absolute value of x plus 3 less than 7. So let's take this one. So absolute value of x minus 3 is always less than 7. Absolute value of x minus 3 is always less than 7. So on the place of x minus 3, we can substitute 7. So absolute value of x squared minus 9, which is equal to absolute value of x minus 3 times absolute value of x plus 3. So absolute value of x minus 3 times absolute value of x plus 3, which is absolute value of x plus 3 is less than 7. So which is less than 7 times absolute value of x minus 3. Which is less than which is less than epsilon, which is less than epsilon, which is less than epsilon. So that 7 times absolute value of x minus 3 is less than epsilon. So that absolute value of x minus 3 is less than epsilon over 7, which is another delta. Therefore, finally, we choose delta will be the minimum of the first choice 1 and the second choice epsilon over 7. So substituting absolute value of x squared minus 9, which is equal to absolute value of x minus 3 times x plus 3, which is absolute value of x minus 3 times absolute value of x plus 3 by definition of absolute value, which is less than 7 times x minus 3, then which is less than 7 times epsilon over 3, so which becomes epsilon. Yeah, clearly absolute value of x squared minus 9 is less than epsilon. So whenever 0 less than absolute value of x minus 3 less than delta, it follows that x squared minus 9 is less than epsilon. Therefore, the limit of the function x squared as x approaches to 3 is 9. So it shows that the limit as x approaches to as x approaches to a of x is a. So using the definition of the definition of limit, let epsilon greater than 0 is be given. Then we must find delta greater than 0, such that 0 less than absolute value of x minus a less than delta implies absolute value of x minus a is less than epsilon. Clearly, choosing delta is equal to epsilon is their choice to make this statement true. So 0 less than absolute value of x minus a is less than delta implies absolute value of x minus a is less than epsilon. So clearly, it's the equation. So delta is equal to epsilon is a correct choice. The other one is basic limit terms. Basic limit terms. So given that the limit of the function of x and the limit of the function of x exists at x approach to a, then the limit of the constant is a constant. Clearly, the limit of the constant is a constant. The limit as x approaches to a of x is a, and the limit of the sum of these two functions is the sum of the limits. And the constant times the function, the limit of the constant times the function is the constant times the limit of the function. And the fifth one is the limit of the product of functions, the product of their limits. And the sixth one is the limit of the quotient, is the quotient of the limit, provided that the limit of the denominator is different from 0. And the limit of the power is the power of the limit. The limit of the power is the power of the limit. So we have these examples. The limit as x approaches to x to the power of 5 minus 9x cubed plus x minus 11. The limit as x approaches to 0 of the square root of a, or 1 plus x minus the square root of 1 minus x over x. And the limit as x approaches 2 of x cubed plus 2x squared minus x minus 2 over x squared minus 4. And the limit as x approaches to 0 of x cos x over x squared plus cos x. And the limit as x approaches to 4 of 1 over x minus 1 minus 1 over x squared minus 1. So to find the limits of the function, we use different techniques. The first one is direct substitution, if it's defined. The second one is if it has radicals or something like that, we can rationalization. The third one is if it is possible to factorizing and canceling common terms. And the other ones are. So we use different methods or substitution techniques. So clearly, polynomial functions are the limit of a polynomial function is obtained by direct substitution. So the sum of the limits is the limit of the sum. The limit of the sum is the sum of the limits. So finding the limits of each of this one will give the limit of the original function. So the limit, the second example, the limit as x approaches 0 of the square root of 1 plus x minus the square root of 1 minus x, clearly over x, clearly at x is equal to 0, it's defined, so that rationalizing by the numerator, by the rationalizing factor, we can see that it's a rationalizing factor. So if this one, the square root of 1 plus x over minus the square root of 1 minus x, so clearly this one is negative, so that you will use rational factor class. So after multiplying by the rational factor 1 plus x minus 1 minus x over x times the square root of 1 plus x plus the square root of 1 minus x. So what's left here is this one will be cancelled by this one. What's left is x plus x is 2x over x times the square root of 1 plus x plus the square root of 1 minus x. Currently, this x will be cancelled by this x. So what's left is the limit as x approaches to 0 of 2 over the square root of 1 plus x plus the square root of 1 minus x. So when you substitute now, the denominator is not undefined, so that 2 over 2 becomes 1. The next one is the The next example is the limit as x approaches 2 of x cubed plus 2x squared minus x minus 2 over x squared. So let's factorize this one and let's cancel similar terms. So since the limit as x approaches to minus 2 of x squared minus 4 is 0, so we cannot apply directly. So using the quotient term. So let's factorize the numerator. So x squared plus 2x squared minus x minus 2 can be written as x plus 2 times x squared minus 1. And x squared minus 4 can be written as x plus 2 times x minus 2. Therefore, the limit as x approaches to minus 2 of x cubed plus 2x squared minus x minus 2 over x squared minus 4, which is equal to the limit as x approaches to minus 2 of x plus 2 times x squared minus 1 over x plus 2 times x minus 1. So which terms are similar? So cancelling those terms which are similar. So what's left? So the limit as x approaches to minus 2 of x squared minus 1 over x minus 2, which is equal to, so now the denominator is not 0, so that we can factor, we can directly substitute the value of x is equal to minus 2. So it becomes 4 minus